With the naked eye, we can make out a few thousand stars in the night sky, as humans have done for many thousands of years. Because they're so many light years away, they seem to be no more than tiny points of light. Gravity binds stars together over enormous distances, gathering them together into vast formations called galaxies. This is our disk-shaped galaxy, the Milky Way, seen from the side, which contains 100 billion stars. The dark areas are immense clouds of gas and dust called nebulae, which are distributed throughout the Milky Way. Earth is located near the outer edge of the flat-shaped galaxy. The distance across the galaxy's diameter, 100,000 light years. Ever since humans began to study the cosmos, we have looked at the stars. Scientists examine most closely that star which is nearest to planet Earth, the Sun. Although it seems eternal, it will not last forever. It has a star's life cycle. It has a beginning and an end. The Sun, like all stars, is a giant incandescent ball of gas. Its surface is not solid, it's gaseous. The gases are mainly hydrogen and helium. Violent internal chemical reactions keep the surface gases constantly churning and erupting. When compared to other stars, it's an ordinary star of medium size. Nevertheless, its size is gigantic. Its diameter of 860,000 miles is over 100 times larger than that of the Earth. Its mass is over 3,000 times greater than Earth's. Surface gravity is 28 times greater than that on Earth, and its age, like Earth's, is 4.6 billion years. The Sun spews gases deep into outer space. This type of curved eruption, which explodes far out into space, is called a prominence. Its arcing form is shaped by powerful magnetic field lines, and its light is from charged particles trapped inside. The prominences flow along the field lines of local magnetic disturbances. They originate and terminate at the local magnetic poles. And periodically, many such magnetic disturbances rage across the Sun's surface. The forces are so powerful that prominences can be catapulted as far into space as would reach from our Earth to our Moon. Sometimes, after just a few hours, the gases fall back into the Sun when the magnetic field suddenly collapses. Other times, the prominences may float in space for weeks. Of all solar eruptions, flares are the shortest, lasting only minutes, and the most violent, created by nuclear fusion explosions equal to millions of hydrogen bombs. So violent that, like earthquakes, pressure waves race across the surface of the entire Sun within a few hours. Superheated columns of gas from the interior constantly bubble up into the exterior layer of gas, the photosphere. There, it cools off and sinks back below the surface the way boiling water does. Although each of the rapidly rising and falling columns of gas measure about 780 miles across, scientists call them granules because they look like granules in boiling water. Sunspots are giant surface eruptions of gas triggered by magnetic disturbances. Many are much larger than Earth. Their centers photograph darker because they're cooler than their surroundings. The Sun is not an especially hot star. The temperature of the photosphere, the surface gas, is about 5,500 degrees centigrade. But gases spewing up from the interior are much hotter. Prominences are 20,000 degrees and flares 100,000 degrees centigrade. For unknown reasons, the corona, gases ejected the farthest out, reach a temperature of 1,000,000 degrees centigrade. But the highest temperatures can be found in the Sun's interior. Its core is about 15 million degrees centigrade. At that temperature, hydrogen nuclei are traveling so fast that when they collide, they fuse together, forming new and larger nuclei, those of helium. This continuous process of thermonuclear fusion liberates enormous energy, which radiates out to the Sun's exterior and then far beyond, traversing our entire solar system at light speed in 5 hours before heading out into the wider universe. Light visible to us is only a small part of the Sun's radiation. But computers can convert the invisible radiation into visible images, like these of ultraviolet light radiation, which reveals solar activities otherwise unknown, or like these of high-energy gamma rays emitted by some very violent eruptions. Electromagnetic radiation stretches from the highest energy gamma rays with the shortest wavelength, next the penetrating X-rays, ultraviolet radiation, then visible light with its spectrum of colors, to infrared radiation, and radio waves, the longest. The Sun violently converts 600 million tons of hydrogen into helium every second, which releases as much energy as 1,000,000 exploding hydrogen bombs. Still, there is enough hydrogen to last for another 5 billion years. Helium has been accumulating in the core where the fusion reaction is happening. The Sun's fierce radiated energy comes predominantly from these nuclear reactions in its core. Some 5 billion years from now, when the hydrogen in the core runs out, the fusion process will change. The core will have become converted into helium and contain no more hydrogen for the fusion reaction. But there will still be plenty of hydrogen surrounding the core, where fusion will continue in an ever-expanding sphere. The core will then be enclosed in a shell of continuing fusion. This is the stage of a star's life cycle known as shell burning. The outward pressure from the increased radiation and gas will cause the dying star to swell. To better see by how much that would be, let's view the Sun within the solar system surrounded by its orbiting planets. The equal balance between the inward pull of gravity and the outward pressure of gas and radiation that had kept the Sun stable for 10 billion years will be coming to an end. As the outward pressure relentlessly increases, the outer layers of gas are compelled to expand, and the Sun begins to swell. It is postulated that 5 billion years from now, the Sun would first engulf planet Mercury, then Venus. It is now inflated to hundreds of times its original size and become a red giant star, and has taken 500 million years to do that. And then it is foreseen that the star will eventually expand to encompass the Earth's orbit and Earth itself. The red giant will then alternately contract and expand with increasing intensity and rapidity. It is changing chemically and structurally, which alternately is causing radiation to increase, which makes the star expand, followed by a period of low radiation, during which the star contracts again. The energies driving this are enormous. The pulsations become so violent when contracting that atoms and subatomic particles are flung far out in all directions. This is the picture of a star nearing the end of its life. Each of these circles of ejected matter is in reality three-dimensional, creating a series of shells enclosing the doomed star. These pulsations continue for millions of years, until at last the star flings off its final and most violent wave of particles, which completely blows away all of the outer layers of matter. Just the core of the star remains. It's only the size of a planet now and is very hot. White hot. And so these star remnants are known as white dwarfs. This is the last phase in a star's life cycle. Our own sun will undergo these changes, first to red giant and then finally to a white dwarf in, it is thought, about 7 billion years from now. With today's technology, we are observing all of these life cycle stages in billions of other ordinary stars, from birth to death. While the time scale of these cosmic events is so far beyond our human rhythms of life as to seem inconceivable, their overwhelming emotional impact does make us feel quite humble.
No, dadgummit.